Up till now, we have set up the boundary conditions, material properties, turbulence model, and report definitions at these point location for monitoring of the convergence of the solution. And we also selected the Kapslon ladder model. And now I'm going to select the remaining settings here, which are the, for example, the solution method. So from solutions and methods, we have the option. By default, now Fluent is giving in the pressure based solver, they are giving the coupled solver. And the difference between simple, simplex and these two remaining solvers that in the simplex, this will solve the continuity and the momentum equation in a sequence. So that's why they are also called the sequential solver. And in the previous version, in the very old versions of the Fluent, like the Fluent 6.1, they called them the segregated solver. So they were the segregated solvers. And then we had the coupled solver. The coupled solver now is known as the density based solver, and that segregated solver, they were known the simple, simplex, and piezo. The piezo is used for the transient problem, and the coupled solver is added later on in the previous releases of the Fluent. And the coupled solver basically solves the problem in a coupled manner. So it will couple the continuity equation and momentum equation and solve in a single matrix. And while these simple equations, they solve the continuity and momentum equation in a loop, and once they both are satisfied, the solution will stop there. And if there is some energy equation enabled or temperature dependent properties need to be solved, then we need to solve the energy equation. So after solving the continuity, momentum, and they are converged, then we move to the energy equation and then turbulence equations. But in the coupled solver, we solve the energy, the momentum, and the continuity equation in a one go. So it may take them more memory, but it will take less iterations. So it is shown multiple times that the coupled solver can solve the problem in maybe 200 iterations or maybe 100 iterations, as compared to simple method, which can solve the same problem, same state problem, maybe in the 10,000 iterations. So that's why they now given the coupled solver as a default option here. And as far as the density based solver is concerned, so in density based solver, we solve all three equations, which are continuity, momentum, and energy equation in a one go in a single matrix. And that solution of the mean quantities will be used for the input for the turbulence model, and then we find out the value of the fluctuation in the turbulence, that is through the turbulence viscosity term in the momentum equation. So anyhow, so coupled solver will be selected here, which is default option here. And if you want, you can have the momentum equation first change to the first order upwind and then to the second order upwind after few iterations. So if the solution is not converging, then you can do that strategy here. I will keep the default setting for the momentum equation. And usually speaking, we solve the turbulence equations with the first order upwind. And in the case when turbulence is important, for example, in water shedding, where turbulence has a major role to play, so I would be selecting the second order upwind scheme for the turbulence quantities. So right now, because the turbulence quantities are not very important, they are important, but with the first order equation, you can get the effects very accurately in the mean equations. And in the controls, we have these terms for the coupled solver. And if you take a look on here, then we have the pseudo transient is enabled. If you turn off this option, you will see that in the controls we will have this current number. So keep the default settings, and if you want, you can try with pseudo transient and without pseudo transient, and keep the default settings for the restriction factors, which are these factors shown here. And then I will go for an initialization. And there are two methods. One is the hybrid, second is the standard initialization. So in the standard method, we can compute data from some constant values or maybe from some boundary conditions. And in the hybrid initialization, basically we solve the very simple differential equation. So this will give you some rough estimate or the initial guess for the solution. And from there, it will carry on to converge solution to the final destination. So if I display the contour plot, so you will see that it will resolve the flow gradients on the geometry in maybe in a better way, maybe as compared to the if we solve with the help of the directly from the inlet boundary condition or with the help of the external initialization. So you can see that when we have the two fluids here, they have the some gradients here. Also in the curvature zone, we have some gradients of the velocity. So it will give you the some very nice basic initial solution. So after initialization, I will go for the also one more important thing is that is to increase the convergence criteria. So by default it's 10 power minus 3. I would be putting the value as 10 power minus 6 or maybe more. So right now it's a 10 power minus 6. So copy this value and paste them in the every field here. And why we are doing it? Because I want that the solution should be stopping when required number of iterations given by me, they are satisfied. Or when I stop the solution by my own command with the help of mouse click on the solution stoppage, and at that moment it should stop. So if we have these low values, so it may converge in a sense that it will achieve this criteria, solution may stop. So because it's a simple problem, so I'm sure the 10 power minus 3 will be achieved maybe within 20 iterations. So I will be doing is that I will increase the convergence criteria to the very tighter values, and I will solve the case up to the values where I'm satisfied. And when I'm satisfied is that when we have the convergence plots, they are now straight lines. So maybe if the convergence criteria is 10 power minus 3, maybe they will stop here. You can see here that it will achieve this value maybe within the 80 iterations. And same is the case with the convergence criteria for the temperature monitors at different 3 points. So that's why I'm putting these high values here. And after that, I will run the solution and put the number of iterations to the, let's say, 500. So 500 is a number, as I mentioned here, that the solution will converge within the 200 iterations might be, or maybe maximum 250 iterations. But I put the value of 500 because that this should run also for the beyond these iterations. So only command or the solution will stop is that when I manually intervene the solution stoppage. So I am just giving the maximum value for iterations and maximum value for my convergence criteria, and now calculate. And now you can see that the solution is now running. And if you take a look here, so with the 500 iterations, so with 40 iterations, around 8% solution is done. And in the scale residuals, you can see that we are achieving the 10 power minus 1 right now for the continuity equation. And for momentum equation, they are already reaching the value 10 power minus 3. And the energy and the turbulence quantities, they are already below the 10 power minus 3 here. And for the monitor plot at the point number 1 for temperature, it is reaching the steady state condition or the converged values. And same is the case with the point number 2 and point number 3. So I will wait for at least 200 iterations. And once these result plots, they are a straight line, they are not changing much. So I will stop there. And here solution after the 180 iterations. These plots are almost straight line, but I'm waiting for the scale residuals to reduce below the 10 power minus 3 or maybe even 10 power minus 4 here. And you can also see that the report definition 0, 1, 2, they are also being plotted on the screen also, and that is to print to console command. And these plots are on the screen, and also we are saving these files in the hard disk as well with these same names. Alright, so now after 250 iterations or maybe 200 iterations, I can see now these plots are now becoming a straight line. And these plots, which are the point plots at some locations of the point, and these are what is average temperature values, they are already converged. So I will stop solution here. So click the stop on the here and stop solution there. So we have the converged solution for the coarse mesh case, and this is the report definition 0, definition 1, definition 2. And if you take a look on the solution here, you can see here that now the solution has been converged. And if I want to solve another case with the medium mesh, so I will just copy this container, and this container has all the settings with it, so I will just change the mesh file. So copying this here and then connecting this mesh file to the new one, I will just transfer new mesh and all settings will be there, and it will solve the case with the same settings here, and stop there after the required number of iterations, or maybe before that we can do it manually. So I will stop here, and the next thing is to post-process results in the Fluent, and in the next section I will be doing it in the CFD post as well.